Okay, welcome to section 4. In this section, we're going to talk about something called binomial distribution. And they're telling us here that we have used the binomial theorem before, which is not actually true. We haven't done the binomial theorem yet, but we still know enough to be able to identify and conduct binomial experiments, and we're going to find probabilities using binomial distributions with a different formula. There's one example at the end we won't get to because we have not done the binomial theorem, but we can get the basic idea of binomial experiments pretty easily. So the vocabulary you need to be on the lookout for is binomial experiment, and binomial distribution. All right, a binomial experiment can be explained with this example. Let's say we have a multiple choice test. Let's say that we have 4 options for each question. If that's true, I can think of each question as a trial with 2 outcomes. And you might say, well, there are 4 options. How can there be 2 outcomes? There are 2 outcomes if we think of it in terms of correct or incorrect. And if you guess on each question, the probability that you answer correctly would be the same for each question. So if there are 4 options, the probability of being correct would be 1 out of the 4, and so the probability of being incorrect would be 3 out of the 4, and that would be the same for every question. There's a 1/4 chance of getting it correct, a 3/4 chance of getting it incorrect if you're just guessing. This is an example of a binomial experiment. Binomial experiments have to satisfy these conditions. There has to be a fixed number of independent trials, n. So on a multiple choice test, that fixed number would be the number of multiple choice questions. And they would be independent because one does not affect the other. Each trial can only have 2 possible outcomes. That's the key to a binomial experiment: success or failure. So just like in my multiple choice situation, even though there were 4 questions, my probability of success was 1/4 and my probability of failure was 3/4. And the probability of success, which we're calling P, has to be the same in every trial. And so the probability of failure would be 1 minus P. So in this case, in our example with multiple choice, my probability of success is 1/4. The probability of failure is 1 minus 1/4, or 3/4. And then the random variable x is the number of successes in n trials. So how many times am I successful over n trials? Let's take a look at this example. We're going to learn to identify a binomial experiment. So here we're going to determine if the experiment is a binomial experiment or if we could make it a binomial experiment. That's what it means by reduced to a binomial experiment. If we can, we're going to describe what one trial would look like, figure out the random variable, and state n, p, and q. Remember that n, p, and q are coming from this here. N is the number of trials, p is the probability of success, q is the probability of failure. All right, so in a class that consists of 12 male and 13 female students, we're choosing 5 students randomly to see how many males are selected. This is not a binomial experiment because these are not independent events. If I choose 1 male student out of the class, then the probability changes for the next time. So the probability of success is not the same for every trial. If there are 12 male students and I choose 1, that probability is 12 out of 13. But then the next time, 12 out of 25, because there's 25 total students. But the next time, so the first time I choose a male student, the probability would be 12 out of 25. But the next time there are only 11 males left out of 24. So my probability of success is changing. So let's take a look at this one. A school study found that 65% of students have seen an episode of Glee. 7 students are randomly asked if they have seen an episode. This is a binomial experiment because each time I ask a student, success in our case would be yes, and failure would be no. So there are only 2 options each time, yes or no. A trial is asking a student, so how do I determine the yes or no? Well, I ask the student. The random variable would be the total number of yeses. Okay, so n, my number of trials, is 7 because I'm asking 7 students. Probability of success, 65%. So that means probability of failure is 1 minus 65%, or 35%, 0.35. Okay, try this one. All right, you should have had A. It is a binomial experiment. Success in this case is thinking that Inception was the best movie. Failure is thinking that it wasn't. So only two options, thinking Inception was the best or thinking it's not. There were 100 trials because we asked 100 people. Probability of success, 38% or 0.38. Probability of failure, 0.62 or 62%. So when I'm conducting a binomial experiment, there are several guidelines. Step 1, I have to describe a trial for the situation and figure out how many trials I'm going to do. Then I have to define what success is, and I have to find the probabilities of both success and failure. Then I have to describe the random variable, and then I have to actually design and conduct the simulation to get the experimental probability. So let's take a look at what this would look like. We're going to conduct a binomial experiment to determine the probability of two fair coins both landing on heads. Then I'm going to compare the experimental and the theoretical probability and see what I can learn from that. So step 1, remember step 1 is describe a trial for the situation. So a trial, one trial is I toss the two coins, and we're going to do 20 trials, let's say. So step 2 is to define a success and find the probabilities of success and failure. A success is both coins landing on heads. The probability of that would be 1/4, and the probability of failure, not both landing on heads, is 3/4. And this one is pretty easy to visualize. I have my first coin. If I toss it, I can either get heads or tails. Then I have my second coin. If my first coin is heads, my second coin could be heads or tails. If my first coin was tails, my second coin could be heads or tails. There's only one situation where I get heads and heads out of 1, 2, 3, 4 possible combos, right? I can have heads, 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 tails, tails, heads, tails, tails. Out of those 4, there's only one that counts as success. Step 3, I need to describe the random variable. My random variable is going to represent the number of successes, right? The number of successes, which in this case is how many times both coins land on heads, because that's how we've defined success in this problem. And then step 4, we're going to use a random number generator to actually conduct this simulation. So we're going to let 0 represent both coins landing on heads, so that's the one we want. 1 through 3 would be any other outcome, and we're going to make a frequency table and record our results. So here, we're imagining that we did that. I'm going to show you the random number generator in a second. So they got 2 heads 6 times, and they got something else 14 times, okay? Okay, so quickly I'm just going to show you on the Inspire how you would do a random number generator. You just have a regular calculator page, and you go to Menu, and then you go to Probability, and you go to Random. So I need a random number generator. We're actually going to generate integers, right? Because we only want 0, 1, 2, or 3. So I put in the lowest value I'm going to go with, which is 0, because we're saying 0 represents 2 heads, and the biggest one I'm going to go with, which is 3. And then every time I hit Enter, it randomly generates a number from 0 to 3, an integer from 0 to 3. So what they did is they just did it over and over 20 times, and you could do this in your calculator too. And then each time they did it, they recorded what they got in the frequency table, right? In the frequency table we have back over here. So they got 2 heads or a 0 6 times, and they got a 1, 2, or 3 14 times. So they just literally made a tally every time they hit enter and checked it out. So the experimental probability of success, if we look at our frequency table, is my successes that I got experimentally, 6 out of my 20 total trials. So my experimental probability is about 30%, and this is larger than my theoretical probability that we calculated at the beginning of 25%. Okay, now we're going to talk about something called a binomial distribution. This relates to something in Chapter 10 that we have not seen yet, which is the binomial theorem, but we have a formula for it that doesn't require us to know the binomial theorem. A binomial distribution is basically a frequency distribution of the probability of each value of x. Remember, x is the random variable. It represents the number of successes that we have in our number of trials. So the probability of x successes in n independent trials is probability of x is the combination of n choose x. So n is my number of trials. X is how many are successful. And then I have p, which is my probability of success to the x, times q to the n minus x. Remember, q is my probability of failure. So the c is a combination, and we'll use our calculators to do that. So again, p is the probability of success, q is the probability of failure, n is the number of trials, x is the number of successes in that number of trials. So let's take a look at how this would work. It says a candy company produces strawberry and vanilla flavored candies, 65% of which are strawberry on average. Okay, so strawberry is 65%. The production line mixes the candies randomly and packages 15 per bag. What is the probability that 7 candies in a bag are strawberry? All right. So we need to find the probability that 7 candies are strawberry, and we're saying a success is strawberry, right? So the probability of success, P, is 65%, 0.65. The probability of failure is 1 minus that, or 0.35. And how many trials am I doing? I'm doing 15 trials, because that's how many candies I'm putting in a bag. Right, so I'm going to get 15 random candies, and I want to know the probability that 7 of those are going to be strawberry. So here's my formula. It looks more complicated than it is. So notice what goes where. Number of trials, 15. X, the number of successes that I want, 7. P, probability of success, to the X, which is 7. Q, probability of failure, 0.35. To the n minus x. So I got this 8 from doing 15, the number of trials, minus 7, the number of successes. And then we just use our calculator. You use your combination button in your calculator to do this. You multiply by 0.65 to the 7th and 0.35 to the 8th. And I get about 0.071, which is about 7% or 7.1%. So the probability that 7 candies are strawberry is about 7.1%. Okay, so you guys try that same thing with this example. All right, your answer should be D, 26.2%. I'll show you how to set it up. All right, so this is what your process should have looked like. Number of trials is 20. X, the number of successes, is 2. I know it seems weird because here our successes, we're saying, are flawed balls, but really success just means that it's what we're looking for, right? So in this case, we're looking for golf balls that are flawed or that have problems. The probability of success, meaning the probability of finding flawed golf balls, is 13%, 0.13. So the probability of failure is 87%, or 0.87. And then we plug into the formula like this. All right, and last but not least in this section, one last formula, the mean of a binomial distribution. So the mean, this is the Greek letter mu, of a binomial distribution is given by mu equals n times p. Again, n is the number of trials, and p is the probability of success. So if they ever ask you to calculate the mean of a binomial distribution, you take your number of trials times the probability of success, and that would be the mean. We'll see if we can do some of those in class. All right, that's the end of this section. Please make sure that you took good notes. Wrote down any questions you have to bring to class, and that's where we will practice.